an exercise comparing those technologies. Namely, I've constructed a distributed simulation model. I will shortly tell about what the model is about, and I've been trying to run this model on two kinds of clusters. So one cluster was placed in Amazon Web Services. It was using AWS Spot instances, which is the cheapest way to buy computing power in the cloud. And the other cluster was a Cray machine. It's on the list of top 500. I think it's now the 300, it has the place 300 in the world. This is the server that has a total of 26,000 cores. I've been using for these experiments up to maybe not the entire Cray machine, but up to 4,000 cores. And I'm going to show you how Julia is scaling. I will start first by very briefly saying about the computational model, and then I move to experiment results. Maybe also manage to show something at the console. Okay, so the model I've been simulating is very classical in social sciences. I've seen some people smiling. So this is Schelling segregation model. So basically, we have two kinds of citizens, blue and red. And the blue citizens like to live together with blue citizens, and the red citizens like to live together with red citizens. If somebody has neighbors of different color, they try to move to a random place on a plane that looks like a chessboard. Okay, so this is very simple. This is very simple model. Surprisingly, no matter from what we start, we always end up with a racial ghettos. So even if you put a very weak preference in this model, you always end up with racial ghettos. So this model can be distributed across several CPUs. So each CPU, so each Julia process can handle a different part of the board. And actually, the only place that the exchange of information happens are the borders, because each agent it's looking at its neighbors. So the only information that needs to be exchanged within this within such cluster is the border information, while the middle of each of the squares can be private to each running process. So we have implemented I have implemented such model. So here's the slightly colored this square, so it was running on 4 processes, and still I could get this racial ghetto patterns. So what was how were the experiments designed? I've used the following layout. So I've been comparing Cray using SLARM, and I've been using Amazon Web Services with very simple cluster management software I wrote in Bash. It's named Keys Cluster. It's like 200 lines of code in Bash and basically no dependencies. So I've been using this to launch the cluster. And now the design was like this. I used to have a control node and a master node and a bunch of worker nodes that were communicating peer-to-peer. They needed to communicate to peer-to-peer to exchange about this border information. So each node was looking, hey, to which neighbors am I supposed to send this information about my border? And they've been doing, and then have been doing it. Now, in case of Cray, there is a different hardware on control node, and there is a different hardware on worker nodes. So basically, I had to build Julia once here, and I had to create another Julia build for the part on the right. So I had to build 2 Julias with 2 different settings. And here's my experience on how to build Julia on Cray. So basically, everything on Cray is very old and doesn't work. So even I couldn't get HTTPS working. So anyway, I've collected my road of pain and just put it as a tutorial. So if you Google for build Julia on Cray, then you can find it on my notes. And if you have any comments and so on, I will be very happy. I will be very happy to update it. And for AWS, I've been using this Keys Cluster library that was written with Bash, and I've used it to manage the cluster. It was the simplest thing I could think of. Okay, it's also on GitHub. Okay, so performance and results, and now I have seen that everybody is doing some demo. So I will try if it's going to work for me. I will at least try to launch computations on Cray. It's sometimes not everybody has been using those strange machines. So it's very kind of risky demo because those things sometimes don't work. So you can see I have here like 1,100 nodes. So these are the nodes, but I will just use 400 cores. Okay, so I need to load those Cray libraries. I need to load GCC, and now I can launch my Julia computation. So this one is configured to use 400. This one is configured to use 400 cores. So currently it's launching all the workers. So I got 400 workers. So I'm using Slarm here. Okay, I'm using Slarm together with this cluster managers.gl. I actually found it very easy and very straightforward to use cluster managers.gl. So it was simple. So let's see if we get the computations running. I think we have already the processes. We have the workers, and now this is always exciting about a live demo. It's like watching horror movie. You never know what happens, but it works. So you can see actually that you have each step of the simulation. So it's already running, distributed on all those cores, and each line here is one step of the simulation. So one generation, all of the agents decide where they move, they relocate, and then goes another and another, and then goes another and another step. Okay, so you can see it's working. So this is what I did, and now what are the Julia performance patterns? So first I started with making plot like this, but of course what's happening in the beginning? Julia is compiling the code, okay? So you know what I mean. So I've cut off the first. The first piece of the time, and then you have then what we can see here. I'm measuring here weak scaling. So weak scaling is I'm making bigger and bigger problem size, so bigger and bigger blackboard size by increasing the number of processes. So for example, what I'm having here the chessboard 4,000 by 4,000. So it's like a place for 60 million agents for each chessboard. And then I'm running this 400 chessboards, 1,000, 2,300, and 4,096. So it's weak scaling. And you can see that the computational time, the computational time is increasing much slower than the size of computational problems. So actually, if you look at this, you can see that Julia scales quite nicely, and adding and moving from like 400 cores to 4,000 cores totally makes sense. So these were simulations on Cray, and I tried to run the same simulation on Amazon Spot Spot instances. So actually, for Amazon simulations, I've been using those C5 instances, and I discovered that a single instance, because they use slightly more modern Intel processors than Cray XC40. So what I discovered basically, when the chessboard, when this board was large, Cray. So here's on this y-axis I have time. So when this chessboard was large, Cray was taking slightly longer to execute, because what's happening, there was plenty of computing and not so much communication, because I've been exchanging only the information on the borders. But on the other hand, when this board I've been analyzing was smaller, so basically then faster communication that was available in Cray was kicking in, and you could see that this inter-node communication was faster with Cray. So to conclude, so I have I have compared these two environments. I'm saying here at parallel just to stress that I've been using all this Julia in-bit parallelism. Actually, the at parallel command was not used, but all the spawn at everywhere and so on macros. So this is what I discovered. So basically, the cost of Spot instances is relatively low, so probably it's applicable for many numerical computations. I do not know how Cray costs. Also, there is another issue that happens very often, and it's not quite handled yet with parallel, is the node failure. So basically, if I use supercomputer, I never have this issue. But running very big clusters of like few hundred nodes in the cloud, basically the failing node becomes an issue because computers in the cloud basically fail more often than others. So one issue I've come through, and maybe this MPI presentation would be solution, and it might be interesting to rerun those experiments, is efficient transfer of data across nodes. So I've seen it sometimes takes too long, and I just said it's the node failure handling. That concludes my presentation. Thank you very much.
Actually, going back to the question that was asked at the end of the last instance, you said that the node failure probability is high in AWS. That's because you're using Spot instances and they're allowed to shut down Spot instances.
No. Okay, so regarding the failure with Spot instances, this is what you said was extremely true like 1.5 years ago, but then Amazon has changed the Spot pricing mechanism. And basically the prices now remain flat almost all of the time. So it used to be issue, but basically now I can rent out a Spot instance, and at least for a few days I can be almost 100% sure I do not lose it. But basically even rent out virtual machine and Amazon, this is something that cloud vendors don't tell you. But basically, if you buy hardware, physical hardware, and you rent hardware in the cloud, the hardware in the cloud has higher probability of failure, maybe because it's a shared instance and so on. And also, even if you look at any kind of SLA or the time between malfunctions, if you run the cluster that has like 100 nodes or 200 nodes, so a single node failure, it's just something that happens in the cloud. It's sometimes people just, used to have a server and then it disappears. Yeah. It happens.
Well, I mean, going back to the last talk, I mean, I've heard it referred to as flock of birds computing, where you have lots of birds flying along doing your computation, and if one of them dives to the ground, it shouldn't matter. The whole thing shouldn't stop.
Yeah. So it depends. So. So basically, it probably would be worth, I've been looking at this, to do some recovery mechanism. Yeah. So like more complicated frameworks have recovery mechanism. But if I just type Julia at parallel, then it stops.
Sure. And do you know that when birds are flying along in a flock, if one of them his second goes down to the ground, two other birds join it because it takes two of them to help it back up into the air. So maybe we need to have two other servers go down and help the other one recover.
Yeah, it could be. So this is about balancing the load and handling node failures.
So I have a question for you. So when you say the node failure probability is high, like do you actually see it in the individual simulation run? Like how often does like one of the nodes crash when you do any particular run?
I've seen it once. So not too many. So you don't see it. You don't see it very often. Like, and then it was like one node out of 200. So it's, and I've also had some stories about people seeing it, or also corporate nodes. But then Amazon provides great mechanisms to recover from failure and to manage that and so on. Also regarding the Spot mechanism, if they are going to take away the server from you, even they have 2 minutes termination notice. So if you can handle this incoming message, then they can pass computations. But then you need to program it and so on.
Let's thank the speaker again. So I have a 1 minute intermission while we get Tamay down here.